头了。不然路上我遇见过不头的，然后我突然想起来，我还有别的我们还可以聊，可怕。休息一下，
of the results. Well, the end of the Spring Festival. So, I hope all of you have already got the notice that homework 3 actually due this Wednesday, as I have explained in the email. If I put 2 weeks homework together, then actually it's going to be a giant homework for the set. It involves 24, 25 problems, and I suppose that would be very hard to manage if you have you are like me, have a stalling symptom, right? And always are pushed back by the deadlines, and I won't be happy to start doing the homework until it is like last 1 or 2 days. Then it's going to be a big trouble for me, because I don't think I myself will be able to get 24, 25 problems done in 1 day. So anyway, so again, if you haven't started homework 3, probably it's a good time to start right now, okay, because we will be as usual on Wednesday weekend, okay? And my goal for today is to close chapter 2, okay? And so by doing that, I'll be first finishing our discussion of the source function for well, not the source function, but well, okay. On the one hand, it's the source function, but on the other hand, it's also the one of the specific solutions that we are dealing with last time. Okay. Well, we finished that part of discussion about how we are going to utilize this fundamental solution to build up, okay, a general solution for general solutions for diffusion equations on the whole real line. And we will also be talking about properties for the diffusion equation, but not on the whole real lines, but on a finite interval. Because by doing that, we will be able to carry out the robustness, including the stability, the uniqueness of the solution, and finally we'll have the detailed comparison between the properties of the solutions to the diffusion equation and the wave equation. Okay, the last part of the class. So first of all, let's try to review. Well, I understand that some of you probably didn't come in the last lecture. It was very cold last week. And if you would like to, well, okay, my class notes is available to everyone, right? And yeah, if you need other source of help, let me know. Okay. So anyway, so for the last time we got when we went through a not so natural route, okay, by first defining a class of properties, okay, by first stating a class of properties for the we were focusing on 2.4, right, the diffusion of the whole real line on the whole real line. And we studied, which was something like ut equals to kuxx, as long as my x belongs to real number, okay, the whole real number. And of course, my 0 is smaller than t, smaller than infinity, okay, and my ux0 equals to things like phi x, okay, which means that we have been talking about an arbitrary. We have been talking about the general solution to the diffusion equation on the whole real line with arbitrary initial condition, right? Because the phi x has not been prescribed before. So we are seeking for a general way to establish the solution to the diffusion equation, okay, for any possible even phi. Okay? And we stated actually a few properties for the solutions, right? If you, so actually the first one, the translation to translative, right? Translative, right? If all the consequences, the requirements for these statements were all that uxt is a solution, to ut equals to kuxx, okay? If uxt is already a solution to the diffusion equation on the whole real line, then translative rule tells you that ux minus yt is also a solution for any given y, for any given y, right? And the second thing is that any derivative of U is also a solution. Okay? And that will include things like UT, UX, UXX, UTT, this kind of things, right? Okay, any derivatives of a solution is still a solution. And the third one is that any linear combination of solutions of, let's say, U1 and U2. If U1 and U2, they are solutions to the diffusion equation, then any linear combination between them is still a solution. Okay? And an extension for 3 is that any integral or any convolution of of a solution is still a solution, which means that let's say if U is a solution, then for any gy, okay, the v xt, which is defined as the convolution from infinity to cos infinity, the integral, the ux minus y t gy dy. Okay, this is still a solution. This is called a convolution. Okay, convolution between U and G. And finally, the last thing. I mean, the first four. Okay, the first four properties, they are actually general. Okay, they're actually general for arbitrary linear partial differential equations. Okay, you can, yes, go ahead.
For gy,
It's arbitrary. It's arbitrary.
Doesn't have to be.
Sorry.
It doesn't have to be a solution.
It doesn't have to be a solution. Gy is arbitrary. So it's, I mean, okay. So for example, for the linear combination. Oh, sorry. It's not so good. For a linear combination. So let's say if U1 and U2 are already solutions, then let's say. Okay, so let me say the following. Okay, so G1 U1 plus G2 U2 is a solution, right? And my G1 and G2, they are arbitrary, right? So the Gy over here is same. It serves as the same role of the G1 and G2 over here, okay? Because they are just the coefficients. They're just the coefficients or weights, okay, for the in the linear combination. Okay. So again, Gy is arbitrary. Okay, and again, all these four properties, they works for any linear, okay, PDE. For any linear PDE. Okay. Well, probably I need to add something that's, let's say, homogeneous. Any homogeneous. I mean, when I'm saying homogeneous, I'm talking about the linear operator LU the linear operator L should send the U to 0. Okay, which means that the right hand side should be 0. And if the right hand side is non-zero, for example, something like GX, then it doesn't work. Okay, these things doesn't work. But here, this is actually UT minus UKUXX equals to 0, right? And the left hand side is a linear equation operator, and the right hand side is 0. So this type of equation is a homogeneous equation. Okay, but that's another topic, and I would like to stop right now. Okay, and the last property actually is a specific property that only works for the diffusion equation. Okay, which is the following: if UT is already a solution, then the dilated solution. Okay, sorry, then the dilated function of U, okay, is UXT is directly defined as U square root of A x and at. Okay, this function is defined as the dilated function of U. Okay, then this guy is still a solution. So is still a solution. This guy is still a solution. And of course, you are already familiar with this, so I will be saving the deduction again. And last time we utilized these properties from 1 to 5, and we started from a very particular initial condition, right? Which was something like, okay, what I got? Let's say Qx0 equals to 1 for any x that's larger than 0, and okay, larger or equals to 0, and 0 for any x that's smaller than 0, right? And then we were seeking for the solution for Qxt that satisfied that Qt equals to Qxx, right? And so because you see that the initial condition satisfied okay, so the route that we gone through was the following. So you see, since our Q actually is satisfied the initial condition, it satisfied the dialectic rule, which means that let's say if my Q xt is already a solution, then my Q square root of ax and at according to my number 5 property, that should be also a solution. However, these two solutions, they share the same initial condition. These two solutions, they share the same initial condition, which is this. Okay? And if we are assuming, if we also assume the uniqueness, okay? If we assume the uniqueness of the solution, then we are able to derive that, okay, the Qxt should exactly equals to Q square root of ax at, because these two things, they are both solutions. Okay, they are both solutions to the diffusion equation on the Holder line, and they started exactly from the same initial condition. Okay, so if we are assuming the uniqueness of the solution, then from the same initial condition, we are only able to obtain one specific solution. Okay, which means that now these two things, they have to be they have to be identical to each other. Okay, they have to be identical to each other, and that means that actually we are able to. So let's say if we are drawing, if we are concerning, if we are concerning the solution, the half length t and x, actually not the lower half, because my t cannot be smaller than 0, right? Because only the solution is only defined on half of the time. Okay. If we're having that, that means that the characteristic lines, I didn't use this word, characteristic lines. The characteristic lines, will be exactly all of the quadratic functions. Okay, will be exactly all of the quadratic functions for the hypotenuse. Will be this, okay? Will be this. Will be this. Will be this. And will be this. Okay, these are the characteristic lines. And again, on the characteristic lines, the solution u should stay as a constant. Okay, on the characteristic lines, the solution u should stay as a constant. Okay, then what we are having, what we're having for the q, then what we're having for the q is that, the q, instead of being a function of two independent variables, the q can be simplified as a function of, the qxt can be simplified as a function of p, where my p is x over square root of 4kt, because that means that this actually is reflecting that, t should be on the scale x squared. Okay, t should be on the scale of x squared. Okay, and if we are having that, then having this in mind, this is actually one of the most important properties for the solution, the specific solution Q that we are going to rely on. Okay, having this in mind, then we can finally deduce, after some computation, that I don't want to repeat for this time, and we finally obtain that my qxt, okay, my qxt equals to 1/2 plus 1 over pi square root of pi, and then the integral from 0 to x over the square root of 4kt, and then e to the negative p squared dp. Okay, so we finally arrive to the arrive to such a analytical form, okay, for q. Don't forget that my q is the initial condition, okay? My q is the solution. My q is the solution based on the initial condition that, okay, it is started from 1 and 0. For 1, it is actually the initial condition is this. Okay, the initial condition is this. So this is my x. This is my q, x 0. Okay, this is also called a Heaviside function. This is also called a Heaviside function. Heaviside step function. Okay, this is called as the Heaviside step function because it enjoys the property that it only has a change by going up from one step at exactly at 0, and it is constant everywhere else. It is always 0 on the left half of the plane, and it is always 0 on the right half of the plane. Okay, and so this is the Heaviside function, and so q is exactly the solution of the diffusion equation on the whole line if we start from the Heaviside function, but q itself is not our final goal. Okay, q itself is not our final goal. Our final goal was actually a derivative of q. Don't forget, according to our property number 2, any derivatives of a solution will be still a solution, right? Then we are able to conclude that, okay, another function, okay, s x t, defined as, okay, partial x, defined as partial q, partial x, okay, this will also be a solution. Okay, first of all, this will also be a solution. And my s will exactly be 1 over square root of 2 pi kt, okay, and then e the negative x squared over 4 kt, okay, for any t to be larger than 0. For any t to be larger than 0. Okay? And since you see s is the derivative of q, s is the partial q partial x for any t. Okay, then what about sx0, which is the initial condition? What is the initial condition for x? Sorry, what is the initial condition for s? Okay, for the new specific solution that I am considering. Okay, it should exactly be the partial h, partial x, or partial q x0, partial x. Okay, this guy. And that is to say, the initial condition for s will be the derivative, will be the spatial derivative for the Heaviside function. However, the Heaviside function is actually indifferentiable. Okay, it's actually indifferentiable. Okay, around x equals to 0, and that actually brings us trouble if we are restricting ourselves in the traditional calculus, in the traditional range of calculus. Okay, and here we'll be defining the derivative. Okay, or sx0. Sorry, here actually should be 0. It should be 0. Sx0. Okay, which equals to partial h. Dhx over dt. Dhx over dx, not dt. Sorry. Okay, this guy will be defining the derivative. Okay, will be defining the derivative of the Heaviside function as this. Okay. First of all, you see, over here is a constant, right? Which means that the derivative over here should be 0. Here, again, it's a constant. So again, the derivative over here should be 0. The only thing is that, okay, there's a sharp jump directly from 0 to 1, which means that the derivative over here, okay, the derivative over here around 0 is actually should be infinity. The derivative should be infinity. Okay, so the function is the following. The function is this. Okay, And here, although I can only draw the red line as this large, but this actually should be infinitely large. This actually should be infinitely large. And since you see, this is again the derivative of h, right? The special derivative of h. Therefore, when we are doing the integration, right? When we are doing the integration, let's say, when we are integrating my s x0, okay? When we are integrating my, sorry. First of all, let me, before I proceed, okay? Before I proceed, first of all, let me define this guy as the delta function, okay? Let me define this guy as the delta function. And the delta function has the property, that, okay, it is 0 for any x that doesn't equal to 0, and it is infinity for x equals to 0. This is the first property of the delta function. And the second property, the first property, and the second property of the delta function is that the integration from negative epsilon to positive epsilon for any small or positive epsilon, okay, of my delta x dx should be exactly 1. Should be exactly 1. And that's actually that actually comes from the definition that my delta function is the derivative of the Heaviside step function, right? Because again, as the original function h, so you see, as a delta function is the derivative of h, right? So which means that h is the original function of delta. And since the original function goes directly from 0 to 1, okay, around 0, then so should the integration of my delta function, okay, around 0. Okay. So, which means that my sx, okay, my sx, here, it should be 0, sorry. My sxt, like this, should exactly be the solution to the diffusion equation, okay, based on the initial condition of a delta function. Based on initial condition as a delta function. And we also talked about we have also talked about the interpretation. And so you see, again, this has been a long walk. Last time we actually used more than 1 hour to deduce them, right? This is indeed a long route. But you see, what is the goal? The goal over here is that, okay, so you see what, so let's try to review the paths that we've gone through, right? So we stated a lot of properties, okay, for the solutions to the diffusion equation. And then we focused on we focused on solving the diffusion equation based on a very specific type of initial condition, which is the Heaviside function. Okay. We got that successfully. But again, this is still far from our original goal, which is solving the diffusion equation, okay, with arbitrary initial condition, right? And we choose to not to directly answer that question, but indeed we turn to another specific solution, S xt. Okay. You see, we obtain another specific solution, S xt, which actually starts from an even more bizarre initial condition, the delta x. But you see, and to arrive to don't forget our initial. Sorry, probably not to use the word initial. That's it. Our original goal, okay. Our original goal was to solve my partial was to solve ut equals to k uxx with arbitrary initial condition, right? ux0 equals to phi x. So far, we have already solved the diffusion equation with only 2 types of initial condition, which is the delta function and the Heaviside function. And now I am going to argue that, okay, we will be able to construct the general solution to an arbitrary initial condition simply by the convolution of the S xt. And therefore, I will be defining we are going to define my S xt as the fundamental solution. As the fundamental solution, okay, to the diffusion equation. the fundamental solution to the diffusion equation on the whole real line. Okay, the fundamental solution to the fundamental solution to the diffusion equation on the whole real line, or the book defines it as the source function. This is also fine. Okay, the book defined our SXT as the source function. Okay, and the argument is the following. Okay, the argument is the following. So first of all, you see Sx0. Okay, again Sx0 is a delta function. It's a delta function. And you see, the interpretation of a delta function was that. Okay, so first of all, don't forget the property of the delta function. Let's look at the function graph for the delta function. The delta function means the following. Okay, everywhere else is 0, and all of the mass. Okay, everything, all of the integration, all of the mass only accumulates around 0. Okay, if we regard it as a distribution of certain random variable, that simply means that this random variable has no probability mass away from 0. But this random variable only has all of the probability mass accumulated around 0, which means that this random variable is exactly a constant, which is 0. Okay? And in the sense of the diffusion, equation, that's equivalent to telling something that's equivalent to saying something like the following. So initially, all of the mass are exactly those locates at some place. Okay, and then it's going to diffuse and out and out and out and out and out and out. Okay, don't forget that. What is the shape of SXT? Okay, it is exactly looks like a Gaussian. Well, this is exactly a Gaussian function. This is a Gaussian function and also a Gaussian distribution, which is satisfying that. So this is Gaussian. This is the Gaussian distribution. Okay, this is the Gaussian distribution. And exactly satisfying that the integration from negative infinity to positive infinity, my Sxt dx equals to 1 for any t. Okay, for any t to be larger than 0. For any t to be larger than 0. And also, if we treat, let's say, okay, so let me call my xt. Okay, let me call my xt follows. Okay, let me say my xt follows the Gaussian distribution for 0 and 2kt. Okay, which means that my Gaussian distribution, my xt. Okay, my xt is a Gaussian random variable, and the expectation is 0, and the variance is exactly 2kt. Then what you're going to see is that the PDF, the probability, okay, the probability density function for xt will be exactly Sxt, which is this. Okay, which is this. So, so that means that the solution started from the delta function. Okay, it will satisfy that. Okay, first of all, the mass, the total mass would be conservative. Okay, the mass is conserved. It's going to be 1. The total mass is going to be 1 from the beginning to the end. And secondly, as we can see, when we are treated as a Gaussian function, the variance is becoming larger and larger and larger and larger. So what we are expecting is that starting from the delta function, okay, starting from the yeah, okay, that's fine. So Sxt x starting from the delta function, okay, then the shape of the solution will first of all be starting from a Gaussian with a very small variance, which means that probably most of the mass accumulates around 0, to Gaussians with much larger variance, okay, which is something like this, and something like this, okay, something like this. Okay, this is the property of SXT. This is the property of the solution starting from the delta function. But we still haven't answered our original question, right? How to solve, again, how do I employ my SXT as a fundamental solution? Okay, and how do I use that to equip a general solution, okay, to the diffusion equation with arbitrary initial condition phi x? How do I do that? Well, there is actually, okay, so don't forget that I first of all, again, okay, so now it starts to, okay, now we start to equip, construct. Now we start to construct, okay, u xt for u x0 equals to phi x, okay, with our fundamental solution as xt. Okay? Our goal is to utilize SXT to construct uxt. Okay? You see, everything over here is linear, right? Everything over here is linear. You see, that means that if I have a solution, you see, if I have a solution, first of all, if I have u, sorry, if I have my uxt is a solution based on ux0 equals to phi x, right? Then what is the solution for vx0 equals to 2 phi x? What is the solution if I'm changing the initial condition from vx, from phi x to 2 phi x? Just be 2u, right? And v will just be 2u. Why is that? That is because, again, everything over here is linear. Everything over here is linear, right? If I have a initial condition, if I'm having my u1 x0 equals to phi 1 x, and my u2 u2 x0 equals to phi 2 x, and my u1 and u2, we know that my u1 and u2 are both solutions, are already solutions. Then what is the solution vx0? What is the solution for v that such that its initial condition is something like a phi 1 plus b phi 2? Okay, it's going to be what? Then my vxt should be what? au1 and then plus bu2. Right? So you see, instead of directly constructing uxt from sxt, what about we first try to construct phi x from delta x? Okay? So the new goal is first construct. Okay, first construct my phi x, okay, which this is the initial condition for uxt. For uxt, right? From delta x, which is the initial condition for sxt, right? Because as long as I know how do I construct phi x from delta x, then I will be able to use the same linear combination to construct ux from sx. Is that logic smooth? Okay, is that, anybody has any questions over that? Okay. Again, this intuition comes from the linear property. Okay, this intuition comes from the linear property. Okay, but how do I do that? How do I do that? Well, okay, so I'm going to directly, I will first directly review the answer and then explain, okay, why it is in that way. Okay, so my phi x, okay, my phi x again, this is an arbitrary, linear. Sorry, this is an arbitrary initial condition or an arbitrary function of x, right? This can be expressed as a convolution of the delta function, okay? Which can be written as from negative infinity to positive infinity delta x minus y multiplied by phi y dy. Okay, multiplied by phi y dy. Okay, and now I'm going to explain. Okay, now I'm going to explain what does that mean. Now I'm going to explain what does that mean. So first of all, the interpretation. Okay, so this is a very important convolution law. Okay, important convolution law. So via the convolution law, I will be able to directly make up, okay, phi x by convolution the delta function, okay, with exactly the same phi. Well, how do I interpret? Interpretation. Okay, there are actually several interpretations that we can employ over here. So again, this looks bizarre, right? How do I understand this equation? The interpretation number one is the following. Okay, I just told you that the delta function can be regarded as a probability density function of a random variable such that it is a constant. It's a constant random variable which always takes the value to 0. Right? Okay, so first of all, delta x is the PDF. PDF stands for, again, what was that? PDF stands for the probability density function, PDF. Okay. Delta x is the PDF for x1, which always equals to 0. Okay, x1, which always equals to 0. Again, x1 is now a random variable, but it's just that this random variable has no randomness. It's always going to take 0. Just like when you are tossing a very biased coin, it's always going to land it with its head up. Okay, it's a random variable. Again, x1 is a random variable. There is no randomness. And second, let's say my phi x, okay, assuming because my phi x doesn't have to be satisfy the axioms for probability. For example, my phi x is always larger than 0, and the integration of my phi x is integrated up to 1. But again, let's just assume that. Let's just assume my phi x, okay, my phi x is already a solution to the my phi x is already a solution. Oh, sorry, my phi x is a PDF for another x2, random variable x2. So far so good. Then, first of all, what is x1 plus x2? Can you please tell me what is x1 plus x2? x1 is a random variable, but that's always 0. x2 is also a random variable. What is x1 plus x2? A random variable plus a 0. That is going to be the same thing, which is what? Same as x1 or 2. x2, right? Again, my x1 is 0. Anything plus 0 is still 0. It's quite good. But how do you express the PDF for two random variables adding up together? I know the probability density function for one random variable, which is delta x. I also know the probability density function for the other random variable, which is my phi x. How do I express the probability density function for their sum? That's exactly the convolution, right? That should be exactly the convolution, okay? So the PDF for x1 plus x2 should be exactly the integration from negative infinity to positive infinity, which is delta x minus y, phi y, okay, dy. So far, so good? So far, so good? And what is the PDF for x2? What is the PDF for x2? Again, by the definition, that should be my phi x, right? So they are the PDF, they are the probability density function for exactly the same random variable. That's why the left hand side equals to the right hand side. Okay, so this is the first interpretation. This is the first interpretation. So this is my interpretation A. Okay, this is my interpretation A. And my interpretation B. Oh, by the way, since you see my my x1 plus 2, of course, it equals to x2 plus x1, right? It's commutable. So this can also be written as from the integration from negative infinity to positive infinity, okay, phi x minus y delta y dy. So it's a bit phi x minus y delta y dy. Go ahead.
Why is phi x necessarily PDF? Because I don't know.
Say it again. Say it again.
Why is phi x necessarily a PDF? Is
It doesn't have to be. Yes, indeed, it doesn't have to be. But I'm just assuming that my phi x is a PDF for certain random variable. Indeed, okay. First of all, my phi x doesn't have to be positive at all. It can be a negative function. Okay. Second, my phi x doesn't have to integrate up to 1. It may integrate up to 2, or it may have an infinite integral. Indeed, that's right. I'm just here the interpretation. I'm just using the interpretation to help you to verify that indeed, okay, the integral. I mean the integral the convolution law is correct. I'm just trying to use the interpretation to help you to understand that. Okay. So this was my interpretation A. And what about the interpretation B? What about interpretation B? Okay. So again, that will be based on the equation that we have written over here. Right? Okay, my phi x can either be expressed as the convolution delta x minus y phi y, or the other way, phi x minus y delta y. Okay. If we were talking about, you see, if we were talking about the first one, okay, if we were talking about the first one. So the problem is that how do we understand? So we already know that my delta x. Okay. So the key to understand, the key part to understand the first equation is to understand what is delta x minus y. Right? We were just writing that down. We were just writing delta x minus y down, but we didn't know how to interpret what is delta x minus y. Okay. So don't forget. This is my delta function. This is my delta function. Okay, is this. Is this. It's everywhere 0, 0, but it's 1. Oh, sorry, it's not 1, but it's infinity at certain places. This is my delta x. Can anyone tell me what should be delta x minus 1? Everything stays the same, but this infinity will do what? Move towards 1, right? So my delta x minus 1 will be something like this. Okay, it's always zero, but the infinity lies over here, lies at x equals to 1. So generally, what is delta x minus y? What is delta x minus y? Okay, so it depends on, for example, so it depends on if my y is a positive number or a negative number or 0, right? If y is 0, then my delta x minus y will be exactly as delta x, the same. If my y is a positive number, then that means that I am simply moving this infinity up to right hand side. If my rightwards, okay? If my y is a negative number, that means that I am moving the infinity to leftwards. Okay? Okay. So now, let's go back to tackle the interpretation of this. Let's go back to tackle the interpretation of this. What does it mean that when I'm integrating? What does it mean that when I'm integrating these two? Okay, now I have something that's say delta x minus y, and another thing which is phi y dy. Okay. So what can I say about delta x minus y? What can I say about the delta x minus y? In most of the places, it is exactly 0. But when it is not 0? Exactly when y, because you see here, what is the independent variable? The y is the independent variable, right? Okay, it's only non-zero when my y goes to x, right? When my y coincides with x. So far so good? So far so good? So that means that this product, to satisfy what? This product for most of the choices of y should be what? Should be 0, because in most of the places, my delta x minus y is 0. So what's good? Okay, but at which place this product is not 0? At which place this product, at what choice of y this product is not 0? Exactly when y exactly equals to x, right? Exactly when y equals to x. Don't forget that so that means that the integration from negative infinity to positive infinity, delta x minus y, okay, phi y dy. First of all, this guy, okay, this product for most of the choices of y, this product will be 0. Only for one choice of y, which is that when y coincides with x, okay, this product is not 0. Okay, this product is not 0. So that means that although you see my phi y is a function of y, but the information contained by phi y is only utilized at which place? At y equals to x, right? My phi y, again, that means that my phi y, okay, my phi y, the inflow of phi y only works when y equals to x. When y equals to x. That means that this guy that means that in this case, my phi y can be regarded as a constant, because again, that means that it's only working in one place, right? That means that my phi y can be regarded as a constant, and that means that it can be extracted as phi x and the integral from negative infinity to positive infinity delta x minus y dy. So far so good? Then what is this integration? What is going to be 1? Right? That's going to be 1. And that's going to be phi x multiplied by 1, and finally phi x. So far so good? So far so good? Okay. So this is the second interpretation. And what about there's going to be a third interpretation? Okay, I'm going to keep interpreting our way to construct, okay, to reconstruct the phi x, okay, to reconstruct the phi x from delta x. Okay, we have been through 1 and 2, but now it's the third one. The third one will be focused on interpreting this path, this path, okay, this path of the equation, which is that what does it mean by from negative infinity to positive infinity, my phi x minus y delta y dy equals to phi x. I'm going to keep on integrating. I'm going to keep on integrating this.
Oh, this is value when just y equals to.
Sorry, say it again.
This is value when y equals to this. Otherwise,
This is going to be like the following. Okay, this is going to be like the following. So, assuming that now my phi is actually can be discreted. Okay, this is something that we are always using when we are doing integration, which is cutting the function into beams, into many small beams, right? Assuming my phi is something like this. Okay, this is my assuming this is my phi x. This is my phi x. This is my x, and I am cutting my phi x into many beams. Okay, my phi x is now in many beams. And, okay, so when I'm talking about phi x, so that means that when I'm talking about, okay, so now, again, I am now looking at this product, the integration of this product. Again, so you see, now the question is that, how do I integrate? So first of all, how do I integrate this integration? This integration, it integrates y, right? But it actually also has a parameter, which is x. I'm integrating y, but there's always a parameter that is something like x. So again, the question is, first of all, when will this product to be non-zero? When will this product to be non-zero? When will this product to be non-zero? Only when y equals to x. Right? Only when y equals to x. That means that after I have selected my x, okay, the parameter x, this integration, this product can only be non-zero. This product can only be non-zero when I am selecting my y to be x. Yes.
now the delta function is.
Oh, yeah, you're right. Sorry. You're right. You're absolutely right. Okay. So, sorry. Let me restate that. Okay. Let me restate that. When I am selecting, after I have selected my x, okay, this product is only non-zero when my y doesn't equal to 0. Okay, when my y doesn't equal to 0. Oh, sorry, it's only non-zero when my y exactly equals to 0. When my y exactly equals to 0. And you see, when my y exactly equals to 0, where is my phi x? Where is my phi x? My phi x is exactly here, right? This is exactly my phi x. That means that this integration directly takes one beam, okay? It directly takes the information from this one beam of phi x and deliver it to the right hand side, phi x. Whenever I am changing my selection of x, this integration is taking the information from different beams, and then finally compose these beams up again, and finally we obtain the original phi x that we want. Okay? So these are the 3 different interpretations about how do I understand this convolution law. About how to understand this convolution. So now you see, originally don't forget that our original goal was to construct uxt from Sxt. To do that, we turn to construct the initial condition phi x from dot x, and we have already known and interpreted, and now we understand what does it mean by that we can construct phi x from the convolution from delta x minus y. The integration of delta x minus y, phi y. Okay? So the question is that, how do I express, now the new question, okay, how to express uxt in terms of sxt. How do I express uxt in terms of sxt? Again, it's a linear. And the way that we compose uxt from sxt should be exactly the same as what? Exactly the same as how do we compose phi x from delta x, which means that here my uxt should be exactly what? I'm going to follow exactly this equation, right? I'm going to follow exactly this equation. My uxt should be exactly what? First of all, the integration from what to what? From negative infinity to positive infinity, and then okay, s, and then what? X minus y. Is that all? T, because s is both a function of space and time, right? And then what? And then what? How did I compose? So here, phi y is actually what? Phi y is actually what? Phi y is, so this integration means that I have different, so there are different versions of the delta function. And I am doing a linear combination of all these delta functions. And the weight is exactly what? The weight is exactly phi y, right? So here, again, when I'm composing my uxt, that means that again, here I have different versions of my sxt by moving the sxt horizontally to the left or to the right. I have many different versions of that. And the weight, again, the weight of each version should be exactly what? Should be exactly my phi y. Right? Okay. Should be exactly my phi y. And dy. So this is the expression. Okay, this is the expression. I'm going to use a big. Okay, this is the expression of the general solution. Okay, for the general solution, starting from a arbitrary initial condition phi x. Okay, which solves the diffusion equation. Okay, which solves the diffusion equation. And you can verify if my uxt is indeed a solution to the original diffusion equation by simply just trying to do the trying to take the differentiations. Okay, you can verify it by yourself. Okay, and yeah, so that's probably okay. So that's probably about it for the first hour, and let's take a 5 minutes break. That's right.
Yes.
Yes.
The integration goes
The integration goes to
back again to 1.
1, but you see, okay. So that means that so that means if I'm only integrating this, okay, not with the weight function phi y, then the integration is going to be 1.
Because phi y times infinity is also infinity.
Okay. You're right. This is actually again about we are having many different infinities, but infinities can also be multiplied and be added to this experiment. This is the problem over here, right? Because again, so this is about so let me try to do that in this way. So again, let's go back to Paterson function. Okay. Now I have the Paterson function. So the Paterson function is my h is my hx. I have my dh over dx equals my delta x. Right? Okay, that means that when I'm integrating over here, or let's say when I'm integrating from infinity plus infinity, my delta x dx, this guy should be 1. Should be 1. Okay, now let's say I'm differentiating two h's. Okay, Okay, then it's going to be 2 delta x. And then you say, this is infinity, right? This is also infinity around 0, but now it's the integration from 2 delta x to 2. Because now this original function is 2 h's. So this is indeed a very tricky part. I admit, this is actually a very tricky part. When you are treating, so this is why that, you see, the book doesn't choose to talk about the solution in that way. Okay, because the book just tells you that, okay, if you compose source function sxt in that way, in the following way, then we obtain the general solution, okay, to an arbitrary initial function. However, this will be, I mean, by introducing, I see the advantage of introducing the idea of L function right now. That will be actually very good for us for later when we go into chapter. When we go to chapter 12, chapter 11, chapter 12, that's going to be very useful for us. Yes. This is how we are composing. This is the solution to the problem. Yes. What not? Yeah. That's right. It doesn't. Yes, it doesn't include. I'm not saying so I'm not saying that we are going to focus on the derivative of UFC here. Okay, I'm just saying that you can just what I said just now. So this is what I wanted to say was the following. So you see now I'm saying that we are observing that UFC is to the initial condition phi x. Okay. If you don't believe that, you can believe that by trying to differentiate, and see if ut indeed equals to k versus. Yeah, this is what I was saying. That's it. The way is here. The way is the high one. Yeah. Because you see, this is how we compose. This is how we this is how we compose phi. Okay, from phi. This is a little bit awkward, but this is indeed how we are composing phi x phi from delta x. Okay, here the wave function is exactly like that. So the same here we're just simply using exactly the same unit combination as the same weights. Wait, we didn't talk about Q, right? Should be S, right?
No, it's the
Yeah, that's right. Yeah, why the condition of Q is involved? Why that is not involved? Okay, because this is because Heaviside function cannot work as a mass function. Because the mass of the Heaviside function is actually infinity. So that's not good. But indeed, the convolution of Qx, okay, the convolution of Qx equals this guy will still be a solution. Well, yeah, it will still be a solution, and you need to find out from that. But what is the initial condition to this solution? Then you will be needing to find out. Okay, so what is exactly this the Q and with y and Qy, right? Don't forget. If I differentiate, you see. If I'm taking the derivative on both sides with respect to x, then what about you first define this guy as an fx? You can just write it as okay, this is my fx, and yes, this is my fx. And you see, if I'm taking the derivative, if I'm taking my t equals to 0, then my fx should be initial condition. Right? Now, if I'm taking, what will happen if I'm taking the derivative? You have to take the derivative on both sides, yes. Now on the right hand side, I just need to take the derivative of Q, right? But what is the derivative of Q? What is the derivative of Q? It's exactly the delta x. T, okay, that's fine, that's fine. Y, right? dy, and yes, and no, there's no other things. We're taking the derivative, there's integration from infinity to infinity and dy, right? And this is integration and integration from infinity to infinity. Because here, we're taking the derivative on x. Here, we also take the derivative on x. Okay? So here we need one more integration from infinity to infinity. Okay? So if I'm taking t equals to 0, what is that?
That's our English, somewhere in German.
I always read the names of them.
Yeah, I think it's called like MF.
Okay, no.
Okay, that's fine. But assuming that you are ignoring, let's say you are ignoring this.
No, I'm going to
Let's say we ignore this one. And let's say now I'm taking t equals to 0. What is t equals to 0? So, okay, so what is x minus y?
You know, there's
That makes more exactly delta x minus y.
Zurich is the same. Zurich formula, like I don't have her back yet, but it's like basically.
Then this integration will be exactly be the convolution of phi y, which will return phi x. So that means that the initial condition. So first of all, this is indeed a solution to the diffusion equation, and the initial condition the initial condition of fx will be exactly the original function for phi x. This is because the Heaviside function is serving as the original function of delta x. Okay. The Heaviside function is serving as the original function of delta x. And when I'm employing the delta x in the convolution, I'm just simply duplicating the original. Okay. So now, if I'm using the Heaviside function in the convolution, I'm effectively integrating. I'm effectively integrating. Well, we also understand this.
Basically, like,
cool. That's a good question. Okay, so these are so far our discussion for the general solution, okay, to the diffusion equation. And let me not be lazy and let me try to write it down again. Okay, the general solution. Okay, the general solution to ut equals to kuxx with arbitrary initial condition that ux0 equals to phi x, where exactly the uxt equals to the integration from negative infinity to positive infinity sxt phi, sx minus y, this must be good, okay, sx minus y t phi y dy. Okay, this is how we compose the general solution to the diffusion equation. And before we dive in the other properties, okay, of the which means that before we get into 2.3, okay, which is the maximum principles and the well-posedness of the diffusion equation, I would like to talk about you know what? Actually, I changed. Sorry about that. I changed my mind. Let me try to do that at the end of this class instead of right now. Okay. So now let's go to 2.3. Okay, now let's go to 2.3. So this is everything that we have talked about for 2.4. But don't forget that 2.4 is the solution to the diffusion equation on whole real line. Okay, and we chose to do that because in this case, okay, the solution will be easier to be expressed. Okay, and everything that we care about is only is only the delta functions and the convolution of the delta functions, and then hereby the source function, the convolution of the source functions. That's all. Okay, that's everything that we need to care about. And however, if we are turning to the well-posedness of the diffusion equation, then we would rather focus on the diffusion equation on a finite interval, which means that besides the initial condition, we'll also be talking about a boundary conditions. Okay. So now let's talk about the diffusion equations. So now it's not going to be the 2.3. Okay, the diffusion equations, the well-posedness. Okay, well-posedness. The well-posedness of diffusion equations okay, on finite intervals. Okay, so don't forget, when we don't forget that when we establish the fundamental solution to the diffusion equation on the whole real line, the deduction of Q, okay, over here, we actually utilize the property that we assume, as you see here, the QXT, it has exactly the same initial condition as its dilated version, which is Q squared of AX at AT, right? In that step, actually we assumed the uniqueness of the diffusion equation, okay, which means that if we are having two different solutions starting from exactly the same initial condition on the whole group, okay, on the version of the whole group line, then we assume that the solutions are unique, which means that only by which we could deduce that my QXT is exactly the same as Q squared of AX and AT. Okay. Now don't forget we assume that. If that is not true, okay, then this step will be invalid. If this step is invalid, that means that I won't be able to have a very nice form for Q, which means that I won't be able to solve the diffusion equation, okay, for this specific type of Heaviside. For this, I don't have this nice solution, okay, to the diffusion equation with the specific initial condition, which means that this step will also be invalid. Which means that everything that we have just said in the last hour and also the whole last class will be garbage. Okay? You see, everything that we have talked about depends on the uniqueness. Okay? Depends on the small uniqueness. Without that, nothing that we said will be valid. Okay? So now is our time to pay our debt. Okay? That's exactly the reason that we first talked about 2.4 and then talked about 2.3, because there won't be. Now we are having a very specific goal, right? Which is pay our debt. Okay, which is that now we need to establish the well-posedness. Now we indeed need to establish the well-posedness. Okay, for the diffusion equation. Otherwise, okay, we have been wasting our time for about 2 or 3 hours. Okay. So the well-posedness, okay, the whole goal, the overall goal for 2.3 is the well-posedness, and it's going to be divided into 3 parts. We will first establish a maximum principle. Okay. So before that, let me first state the question right now. Okay. Again, we are talking about the diffusion equation, which is ut equals to kuxx. Okay. But it is now on a finite interval. So we are assuming that now my t again is larger than 0, but my x, instead of residing on the whole real line, okay, my x is now only defined between 0 and L. My x is now only defined on 0 and L. Okay. The reason that we choose to do this, okay, is that we are able to introduce the boundary conditions. Okay. Then we are able to introduce the boundary conditions. And the boundary condition for the solutions on a finite interval is actually it is a little bit anti-intuitively. It is a broader way of illustrating the diffusion equations. Okay? And what you're going to see is that the method that we're going to use to establish the uniqueness and the sort of the well-closeness for the diffusion equations defined on the finite interval, it will also automatically, okay, it will also automatically be useful for the case that when my x is defined on the whole real line. Okay, so we will first establish the well-closeness for the diffusion equation on finite interval, and then, okay, it will be actually a very easy. It will be actually a very easy job for us to return to the infinite for the solutions established on the whole real. Okay. So maximum. So we are going to establish the question. So first of all, ut equals to kuxx, and then the initial condition. Again, it's ux0 equals to certain things like phi x, but don't forget that now my initial condition my x can only be within 0 and L. There is one more thing, which is exactly the boundary condition. Okay, which is exactly the boundary condition. And in this case, let me say my boundary conditions there are two boundary conditions, u0 t, okay, equals to, so the boundary conditions will be things like, okay, on 0t and on lt, which means that, you see, if I'm drawing my solution, okay, this is my x, this is my t, so this is going to be my initial condition. Okay, this is 0, this is L. This is going to be my initial condition. My initial condition will be an arbitrary function over here. So what's that? And this is going to be my boundary condition. This is going to be my boundary condition. Okay, this line is, all the points on this line is going to be 0t. And all the points on this line is going to be lt. So that's good. These two blue lines, okay, are my boundaries. And the boundary conditions, and here, you see the initial conditions, it resides on the x-axis. So it's a function of what? It's a function of x, right? It's a function of x. And the boundary condition, it lies on what? It actually lies on the t-axis, or be parallel to the t-axis, right? So my boundary function should be a function of what? My boundary condition should be a function of what? My initial condition is a function for x. Simply because the initial condition is on this is on the x-axis. My boundary condition is on the t-axis, or parallel to the t-axis. So my boundary function should be what? Should be functions of t, right? My boundary conditions should be function. Okay, function of t. And let me not specify that for now. Let me not specify that for now. And the maximum principle, okay, the maximum principle is the following. The maximum principle is the following, okay? So now I'm going to state the maximum principle. Okay? Let's say my uxt is a solution, okay, to the diffusion equation ut equals to k uxx, okay, on a finite interval for t be larger than 0 and x to be within 0 and L. With arbitrary initial conditions. This is my IC, okay, this is my BC, and boundary conditions. Okay, again, I'm not specifying, this is exactly the reason that I'm not specifying my initial condition and boundary condition. Okay? So assume that my uxt is a solution to the diffusion equation of this finite interval, and my initial conditions and boundary conditions are arbitrary, they can be literally anything. then let's say, and well, okay, and let me specify the range of t. Let me specify that my t also belongs to something like 0 and 80. Okay, because now I don't like to pursue the solution on the whole for all the time. Let's say I'm just keep solving the partial differential equation until I'm getting to 17. Okay. So if I'm having that, then in the temporal let me see. Okay. Then in the space-time domain, okay, in the space-time domain, okay, which is x t belongs to the product of 0 and L multiplied by 0 and t. Okay, this is going to be my space-time domain, right? Say this is now t. This is t. Okay, this rectangle is going to be my space-time domain. My x is defined between 0 and L, and my t is defined between 0 and t. Okay, this is my space-time domain. Then in the space-time domain, this rectangle, the maximum value of uxt, okay, can only be, is assumed, okay, is assumed either initially, which is t equals to 0, or on the lateral side, which is x equals to 0 or x equals to L. So what does that mean? Let me try to re-say that. So you see here, my uxt is defined in this rectangle, right? My uxt is defined in this rectangle, and for every choice of a pair of xt, I'm going to obtain my uxt, which is the function value, uxt, right? The maximum principle states the following, that the maximum is attained either here or over here. It cannot be anywhere else. The maximum cannot be attained inside. The net maximum cannot be attained here on top. The maximum of the whole uxt on the whole domain can be only attained either here or here or here. So that is the message is very clear, right? The message is very clear. The maximum can be only obtained on the boundaries. Either the spatial boundary or the temporal boundary, but only the initial temporal boundary cannot be obtained on the end. And that's actually not so hard to understand intuitively, because now we already know what is the solution to the diffusion equation, right? Because you see, for the solution to the diffusion equation, it satisfied what? It satisfied that originally, you see, if I was a delta function, then it melts down initially. So it melts down instantly, okay, and then it keeps going and going, and the heights. Don't forget where was the here, right? Initially, it was everybody accumulates at the same place, right? And then it melts down, and then goes down. Right? It smooths everything. It smooths everything. If I'm having two, so if initially I am having two things like this, okay. Okay, so for example, this is my 0, this is my L, this is my 0, this is my L, this is my U at x0, if this is my ux0, okay, and I'm having more mass accumulated at L instead of 0, okay, then what will happen? We would expect that the mass will diffuse from right to left because of the gradient, right? And finally, it's going to be something that's it's just becoming flatter and flatter and flatter and flatter and flatter and flatter, right? So in this case, the maximum is attained at which place? At L, but initially at 0. At any constant, or at any other time points and spatial points, okay, none of these choices of xt can obtain a function u xt that is larger than this guy, because initially we was highest and then melts down and melts down and melts down, and then finally, everybody just is balanced. Okay. So this is actually not so hard to understand. This is actually not so hard to understand. But again, this is a a mathematical class, right? Probably better we do closer. So this is a mathematics class. So indeed, we need to prove this, okay, in a more rigorous manner. We need to prove this in a more rigorous manner. And you see, what we are going to do is going to prove by contradiction. Okay, proof by contradiction. Okay, let's say that the maximum is attained over here at a certain interior point. If the maximum is attained at certain interior point, then what can I say about it? Assuming that, you see, assuming that my uxt is adequately differentiable, which means that it's a, let's say it has arbitrary order of derivatives according to your calculus class. What can I say about my uxt if its maximum is attained over here in certain interior point instead of on the line? What can I say? What can I say when a certain point is a maximum? Okay. For 1D function, here is the maximum. What can I say? This derivative, what derivative? This first order derivative should be 0. Okay. If this is my fxt, so this is my, because we are still talking about 1D, right? If this is my fx, I have my f prime x 0. Okay, let's say this is my 0, which obtains at maximum. I have my f prime x 0 equals to 0. But is that enough? Is that enough to guarantee a maximum? What about something like this? What about this? Minimum still has a first derivative to be 0, right? And a neutral point like this, it still has a first order derivative to be 0. Right? What else do I need to guarantee that it's the maximum? The second order derivative should be what? Should be what? Should be negative. The second order derivative, f prime prime x 0. Well, because it doesn't have to be a unique maximum, right? It doesn't have to be a unique maximum. So its second order derivative can be 0. Smaller or equals to 0. It doesn't have to be strictly negative. Okay, it can be 0. The second order derivative can be 0, but it has to be at least it cannot be positive. Right? At least it cannot be positive. Only by that, okay, we can guarantee that there is a maximum. Okay. Now you see, this is not a maximum. This is a maximum not for a 1D function, but for a 2D function. This is a maximum for a 2D function. So applying what we have obtained over here, and we erase this guy. Okay. Applying all the intuition that we obtained over here, what can I say for a maximum value, okay, in certain interior of a 2D function? xt. Okay, let's say we obtain the maximum at x0, t0. This is x0, t0. What can I say? First of all, again, because you see, the maximum means that on this intersection, okay, this is a 2D function, but on this intersection, it's still a 1D function, right? On this 1D section, it's still a maximum, right? Well, on this 1D section, it's still a maximum. On this 1D section, it's still, again, it's still a maximum, right? So this argument can work for what? Either x and t, right? Because again, the logic is that, you see, on the x direction, this is the x direction, it's a maximum. It's a maximum. And on this direction is also a maximum. On the t direction is also a maximum. So that's good? So again, maximum requires that first order derivative to be 0 and second order derivative to be smaller or equals to 0. So what can I say about the first order derivatives and second order derivatives for the around the maximum? What can I say? What can I say about specifically? What can I say about ut x0 t0? What can I say about this? It has to be 0, right? It has to be 0. Because again, see, what is ut x0 t0? It's going to be evaluated on this direction, right? It's going to be evaluated on the vertical direction. But again, this is again indeed a maximum on this direction, right? On this direction. So the derivative, first order derivative on this direction should be 0. So far so good? So far so good? What can I say about ux x0 t0? What can I say about this? Still 0, right? Because again, it's a maximum on this direction. What can I say about uxx x0 t0? Okay, ux is the second order derivative. Okay, according to this, it should be what? Should be smaller or equals to 0. Should be smaller or equals to 0. So far so good? So far so good? But don't forget what is the diffusion equation about? Okay, so now you see. So the idea to prove. Okay, the idea to prove the maximum principle is exactly like the following. So any interior maximum would lead to, would yield automatically that, ut x0 t0 to be 0. ux x0 t0 to be 0. And uxx x0 t0 to be smaller or equals to 0. But what does the diffusion equation tells us? What does the diffusion equation tells us? My ut should be exactly equals to what? Okay, my ut should exactly equals to kuxx. And that should also satisfy for this, right? That should also satisfy by the ut and uxx evaluated at x0 and t0, x0 and t0. So good? So good? Therefore, if I am able to change this smaller and or equal sign to be a strictly smaller than sign, then I'm done. Because of what? Because you see, if I were, you see, so if we are able to state that uxx x0 t0 to be strictly smaller than 0, then we would have 0 equals to ut x0 t0 which equals to k uxx, but this guy is again smaller than 0, which is actually a contradiction, right? if I'm able to state that the u-axis, the second order derivative, the u-axis is evaluated at the maximum, is strictly smaller than 0, then I'm done, because I have the contradiction. If I have the contradiction, then that means that the premise that my xt, sorry, my uxt obtains a maximum at a certain interior point, okay, this will be invalid. This would be invalid. However, we haven't done that yet, right? However, you see, this based on our if over here, right? If we are able to state that, we haven't successfully done it. Okay, we haven't successfully done it. Okay, so that depends on if we are indeed can successfully exclude the possibility that uxx evaluated at x equal to t0 exactly equals to 0. If we are able to exclude that possibility, then we are able to prove, then we are able to yield a contradiction. The contradiction will in turn help us to vettle the possibility that that uxt obtains its maximum, okay, at certain interval. So this was the idea to prove. This was the idea to prove. Now let's start the strict proof. Okay. Now let's start the proof. Start the proof. Okay. Let me redraw a picture over here. Okay. So this is the initial condition between 0 and L. And this is the boundary, this is the boundary, this is the boundary, and this is at t, okay, this is at t, between 0 and t, okay, this is the x-axis, this is the t-axis, and we are trying to vettle the possibility, we're trying to vettle the possibility that a maximum interior. Okay, so now here's the proof. So now, let n, okay, denote the maximum value of uxt, okay, on the three sides okay, t equals to 0, x equals to 0, and x equals to L. So again, let's say on the three sides, okay, on this side, and this side, okay, on the three sides, the maximum value is n. So that's good. Okay. This side, okay, the maximum value is n. I'm not talking about interior. I'm just saying that n is the maximum on the three sides. Then what does the maximum principle tells me? The maximum principle tells me that then any of the interior point, okay, cannot obtain n, or cannot be larger than n. Any of the interior point cannot be larger than n. Okay? Then we are going to prove our goal, okay? Our goal is to prove that, okay, our goal is to prove that uxt is smaller or equals to n for any xt belongs to the rectangle, and then multiply by 0 and L. Oh, sorry, 0 and t. This is my new goal. My goal is to prove that on any point, any point on this rectangle, okay, my uxt is strictly smaller than or equal to n, as long as my n is the maximum value for u on these three sides. Okay. And again, okay, I'm going to introduce a bizarre way, okay, just to facilitate the proof completely. That's completely for. So what I'm going to do in the next few steps is going to completely for the convenience of the proof. Okay. So now let's say my n, okay, sorry. Let me say my epsilon okay, my epsilon. So now, okay, so this is the step number 1. And step number 2. Let's say epsilon is a positive constant, a constant. Okay, and let me define, okay, Vxt equals to Uxt plus epsilon x squared, and the Vxt is actually a certain, it's a function introduced to help us to do the proof. In itself doesn't have any physical limitation. It's a function that it's a function that we introduced by ourselves. Okay, this Vxt is something that we introduced to facilitate the proof. And you're going to see that the choice of adding u with the epsilon x squared, that's also a certain choice that's changeable. Okay, for example, that can be changed to x cubed or x 4 times other as long as the function is as long as the functions keep going up and it's convex. Okay, but that doesn't matter for now. Let's just say my Vxt is defined as Uxt plus epsilon x squared. Okay, again, this is the function. This is a function that we helped. Okay, this is a function that we introduced to help our proof. Okay, and our goal. So we turn to prove that my Vxt is smaller or equals to m plus epsilon L squared. Okay, for any x and t belongs to the rectangle. Let me define my rectangle to be R. Okay. Okay, this is defined as R. Okay. Again, R for rectangle. Or R. Okay. So you see. Again, let me try to say this again. See, so first of all, I have my Uxt, and my goal was to prove that my Uxt attains its the maximum of the Uxt on the whole rectangle is exactly my m. Okay, and you see, my Vxt is what? My Vxt is the Uxt plus a epsilon squared, So if my Uxt is satisfied by m, if my Uxt is bounded by m, then what is the maximum of Vxt should be what? The maximum should be the maximum of this plus the maximum of epsilon x squared, right? But what is the maximum of epsilon x squared? You see, x is defined in what? It's defined between 0 and L. So what's the maximum choice from x squared? L squared, right? L squared. So the largest possible value for my Vxt is going to be the m plus epsilon L squared. Right? The largest value for Vxt is going to be m plus epsilon L squared. And the good thing for me, once this is once this is done, okay, if this is done, then we can say that my Uxt is smaller or equals to m plus epsilon L squared minus x squared, right? Because from this equation, my Uxt equals to Vxt minus epsilon x squared. So right, so if I can already prove that my Vxt is smaller or equals to m plus epsilon L squared, then actually that is equivalent to Uxt be smaller or equals to m plus epsilon L squared minus x squared. So far so good. This step is good, okay? But don't forget that epsilon is what? Epsilon is larger than 0 as a constant. Actually, it's arbitrary. It is arbitrary, right? It's a constant that I choose by myself. I can choose any epsilon. I can choose the epsilon to be 1. I can choose the epsilon to be 0.1. I can choose the epsilon to be 0.000001. I can choose the epsilon to be as small as I would like. Right? I can choose the epsilon to be as small as I would like. That means that when my epsilon goes to 0, then what is the right hand side over here for this inequality? When my right hand side is, when the epsilon goes to 0, then this part is going to be what? It's going to be 0. Then I can successfully prove that my uxt is actually indeed bounded by n, which is exactly my original goal, right? Which is exactly my original goal. So that's good. So again, you see, indeed, the v over here is something that we introduced. This is something that we introduced to deliberately help us to prove, okay, to facilitate our proof. Okay, it's going to be abandoned after we are done with the proof. We don't need to think about it anymore. Okay, that's the whole goal of our review. Okay, so now, okay. Okay, so you see, this is our new goal. Okay, so this is our new goal. So now, step 3 is that we need to prove. We need to prove Vxt is smaller or equal to m plus epsilon L squared for any x and t on this rectangle. Okay, now we need to prove this. This is already true. Okay, this is true initially for t equals to 0. Because of what? Because you see, because that is because okay, the function okay, so sorry, this is true. So first of all, this is already true for t equals to 0 and x equals to 0 and x equals to L. Because of what? Because you see, according to our definition of the m, it's already the maximum for the function values on this side, on this side, and on this side. Right? And my definition for my v is exactly m plus epsilon L squared. My definition for my v is exactly uxt plus epsilon x squared. Right? So the value of v should be exactly bounded by m and plus L squared on these 3 boundaries. So far so good? That part is so good? Okay. So this is true for the boundaries. For the boundaries. For the boundaries. Okay. Then also the function, this function v satisfies the following. Okay, satisfy the following. It's actually vt minus kvxx, right? It's kt minus kvxx, which equals to what? Don't forget. Okay, let me write it down over here, right? So don't forget that recall that vxt is defined as uxt plus epsilon x squared. So what is vt? First of all, what is vt? What is vt? ut. Okay. What is vxx? What is vxx? It's it's uxx and then what? Plus what? 2 epsilon, right? Minus k, and then it's going to be uxx and then plus 2 epsilon. So far so good? So far so good? And this exactly equals to what? Because exactly equals to ut minus k uxx and then minus 2 epsilon k. This step is good. This step is good. But what do I know about ut minus k uxx? What do I know about ut minus k uxx? It is 0 because of what? Because u is a solution, right? So that should be exactly equals to negative 2 epsilon k. Okay, 2 is a fixed number. Epsilon is what? Is a positive number that I choose to be positive. K is what? K is also positive. So what can I say about -2 epsilon k? It's a negative number. Can that be 0? Can that be 0? Does it have any possibility to be 0? No, why not? Why not? Because first of all, k is what? K is the diffusion speed. The diffusion speed is defined to be positive, something that's not 0. And also, the epsilon is chosen to be positive. I choose the epsilon to be positive, right? So this is something that's strictly smaller than 0. This is something that's strictly smaller than 0. It has no space, okay? It has no space. It has no possibility for this -2 epsilon k to be 0. And so is my Vt minus kvxx. Right? This is my kt minus kvxx. Okay? So now, suppose, let's suppose Vxt, okay, attains its maximum at an interior point, okay, x0, t0, okay, which is not on the boundary, okay, which is not on the boundary. That is, which this can satisfy that 0 is smaller than 0, also xt is larger than 0 and smaller than L, and t is larger than 0 and smaller than t. Okay, suppose that my vxt, not uxt, okay, I'm changing our goal from u to v. Suppose that vxt attains its maximum at certain interior point. Okay, x0 and t0, not that about 3. Then what will happen? First of all, what is Vt? What is Vt? What is Vt? Don't forget, Vt is defined as uxt plus epsilon x squared, right? And Vt attains its maximum at certain interior point. And what do I know about Vt?
Vt at this point.
Sorry, Vt, yes, you're right. What can I say about Vt is at x0, t0?
Oh, this is
Should be 0, right? We have argued this. Exactly should be 0. Okay, exactly should be 0. What can I say about Vxx at x0, t0? Here, what can I say about Vxx? It should be smaller or equals to 0, right? It should be smaller or equals to 0. Again, this works for what? This works for arbitrary function. As long as this arbitrary function attains its maximum at a certain interior point, this can work for u, this can work for v, this will work for w, this will work for any function. As long as function attains its maximum, okay, in this interior point, okay? Now, what now, you see, since my Vt equals to 0, and my Vxx is smaller or equals to 0, what can I say about Vt minus kvxx? What can I say about Vt minus Vxx? What can I say about Vt minus Vxx? Vt minus kvxx. It should be larger or equals to 0. However, this is what? We have just deduced what? We have just deduced that Vt minus kvxx is strictly smaller than 0 throughout the whole rectangle. Right? We have deduced that Vt minus Vxx is something that's strictly negative throughout this rectangle. So that is a contradiction. So let me say this is my inequality. This is actually the diffusion. This is defined as the diffusion inequality. Okay. So this contradicts the diffusion inequality. Okay, this contradicts the diffusion inequality. That means, so this concludes that, okay, what I have supposed over here, okay, whatever that I have supposed over here is invalid. Suppose that what I've supposed here is invalid. Which means that my Vxt cannot attain its maximum, okay, at an interior point. Okay? But if my Vxt, you see, what is my goal? My goal is that I would like to restrict, this is what I would like to do. I would like to prove my Vxt is bounded by n plus epsilon L squared, right? And we have just shown that the Vxt cannot attain its maximum at an interior point. If the Vxt attains its maximum on the three boundaries, on these three boundaries, then I'm already done. But there's one more possibility that I need to exclude. What is that? On the top, right? What if my Vxt attains its maximum on the top? Then it's still not good for us. Okay. So now, our suppose, this is my suppose number one. My suppose number one has been dealt. Now, I'm going to suppose, okay, this is the first scenario. And the second scenario, suppose that, and this is going to be my suppose number two, okay? Suppose number two, that my Vxt attains its maximum, okay, on the top boundary. Which is my t exactly equals to t, but my x0 should be still within 0 and L. It cannot be the corner, right? Okay, so it's on the boundary. Now I'm supposing that the maximum is attained over here on the top boundary, but it cannot be on the corner because the corner is also shared by the two boundaries, by the two spatial boundaries. Sounds good? Okay, I'm going to suppose that. Then again, my goal is to deduce a contradiction. If I suppose that, then you see, if I suppose that, then first of all, again we are going to have Then again we are going to have Vx. And so first of all, I can't say, you see, if the maximum is attained over here, if the maximum is attained over here, can I still assert that ut x0 t0 equals to 0, x0 t0 equals to 0? If the maximum is over here, can I still say that the time derivative over here is 0? Can I say that? Not necessary, right? Not necessary, because let's say if this is the t-axis, then something is just going up, right? And the maximum is attained over here, right? I can't say that. If that's keep going up, I can't say that the derivative over here is 0, right? But what can I still say? Since the maximum cannot be here, it cannot be here. It's in the interior, not interior of the rectangle, but it's in the interior of this line. What can I still say? I still can say that my ux is 0, and my ux is smaller than 0. This is something I can still say, right? I can still say this. Okay. Then I can still say my Vx, okay, x0, t0 equals to 0, and my Vxx, x0, t0 is smaller or equals to 0, as before, right? Okay. And since my v x0 t0 is actually the maximum, because we are supposing it's the maximum of vxt of the whole rectangle, right? So my vx0 t0 is larger than vx0 t0 minus delta. So I'm just saying that what I'm just trying to say is that, okay, because the function attains its maximum over here, so this value should be at least slightly larger than this value. So what's that? That's the definition of the maximum, right? It's the definition of the maximum. Okay, then we have then vt x0 t0, okay, should be what? Should be the limit of when delta goes to 0, vx0 t0 minus vx0 t0 minus delta, okay, over delta. This should be always be larger or equal to 0. So what does that mean? That means that, you see, so that is to say, if the maximum is obtained in an interior, I can just directly say that the first order derivative will be exactly 0. Okay, ut will be exactly 0. If it's not obtained in the interior, but only obtained, okay, on the top of the boundary, okay, then if it is not zero, then the only possibility will be that this guy is going to be larger than 0. It cannot be anything that's smaller than 0, right? Because if it is smaller than 0, then that's saying that some value over here is even larger than the maximum that I have supposed. So that's good. So now my ut, indeed, my ut x0 t0 is not guaranteed to be 0, but that's guaranteed to be larger or equals to 0. So good. That's guaranteed to be larger or equals to 0. Then what can I say about my vt minus k vxs? Okay, it should be larger or equals to 0. Still should be larger or equals to 0, because my vt is guaranteed to be larger or equals to 0, and my vxs is guaranteed to be smaller or equals to 0. And my k is a positive number, right? So this guy should be again larger or equals to 0. So again contradicts the diffusion inequality. The diffusion inequality. So, to conclude, okay, so to summarize, scenario 1 and scenario 2, both of the suppose both of these suppose are vetted. So what is the only possibility now? My v should attain its maximum at which place? My v can only attain its maximum on the color boundaries, okay, on either the blue or the red, okay, which means that so to summarize our results, my vxt can only attains its maximum, okay, on the boundaries that t equals to 0, x equals to 0, or x equals to L. Okay, if I have that, then I already got that my vxt is smaller or equals to m plus epsilon L squared. Okay, this according to the definition of v, don't forget that my vxt equals to uxt, this is my definition of v, right? And then plus epsilon x squared. Then this tells me that my vxt is, instead of v, actually my uxt exactly smaller or equals to m plus epsilon L squared minus x squared. Okay, since my epsilon is arbitrary, positive number. Okay, I can let epsilon to go to 0. I can let the epsilon go to 0, which means that now my uxt has to be smaller than x to n to make this inequality to be whole, okay, for arbitrary epsilon. Okay, so now this is my final one. Okay, so thank you for everyone. I am over time for about 10 minutes, and sorry about that. Okay, and so this is the introduction to the maximum principle, and in the next class we'll be finishing. I really target to finish the chapter 2 in the next class, but anyway, so because this is actually a very proof extensive for today, and a lot of things to digest. If you are if you're still uncomfortable with certain materials, then you know, and I'm going to be holding office hour in the next hour. Okay. Yeah.